Now that we've sort of been working with limits for a little while and we sort of have an intuitive sense of what a limit problem is asking us to do, let's go through and see if we can define some very concrete properties or rules that we can use when we're evaluating more complicated limit functions. So I'm going to write up here, this is going to be limit properties, or properties of limits if you prefer that. And the first few of these are going to be fairly obvious. So let's start out with the obvious ones and then work down to the more complicated ones. The first one is going to be that the limit as x approaches any value a, as x approaches any value a of just a constant, what is this going to be equal to? This is just going to be equal to whatever that constant is. And you can think about it in the intuitive sense of thinking about it. This is like saying that if we have a function, f of x is just equal to any constant. If we said, f of x is equal to 2, this would just be a line. It would just be a line along the point y, or along the line y is equal to 2, along the line f of x is equal to 2. So therefore, if we chose any x value, if we chose, -3 or 1 or whatever that point is, it's 1, 2, 3, 4. If we chose 4 or any point along x, and we got really infinitesimally close to whatever point it was that we chose, f of x is always going to be approaching the same thing. It's always going to be even equal to the same thing. So therefore, if we chose any value for x, if we said we chose, what is that? That's -3. If we said the limit as x approached -3 of 2, well, that would always just be equal to 2, right? So anyway, that's, I guess, the intuitive sense of our first property of the limit. The limit as x approaches any value a of some constant is just going to be equal to that constant. Next, the second property is that the limit as x approaches a of the function x, what is this going to be equal to? Well, this is just going to be equal to whatever this value a is. So that would be like saying, let me just go ahead and erase this stuff on the graph. And there we go. Almost. There. So this would be like saying we had a function f of x is just equal to x, right? And so that would just be a line. It would be a line that hits the origin and has a slope of 1. Try to... There. Well, that's kind of a sad drawing, but it'll work. So now, if we chose any value for x along that line, and first off, let's just make sure there are no discontinuities along this line. We can plug any real number into x that we want. We can plug pi, we can plug 1,000,000, we can plug any number into x here, and our f of x value is always just going to be whatever that number is. So if we chose 2 here, the function would approach 2. If we chose, what is that? That's 1, 2, 3, 4. That's 5. If we chose 5, the function would be approaching 5 at that point. So therefore, the limit as x approaches a of just the function x, that is going to be equal to a. So now, those are sort of the most basic properties. The next bunch of properties we're going to look at have got to do with functions when we are combining functions together. And the first one, we're going to look at if we took the limit of two different functions, the limit as x approaches a of, let's say, two different functions, f of x plus g of x. And we're going to say down here that f of x and g of x, that the limit as x approaches a of f of x and the limit as x approaches a of g of x, we're going to say that both of these exist, and they're both finite. So that's the rules that we're setting up right now, that both the limit as x approaches a of f of x and the limit as x approaches a of g of x, that both of those exist and they're both equal to finite numbers. They're both, whatever those numbers are, they're both finite. Neither of these are infinity. So what this is going to be equal to is x approaches a. We can actually distribute this limit operator amongst these two functions. And we can say that this is going to be equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So that's like saying, if you've heard it before, that the limit of a sum is going to be equal to the sum of the limit. So we can individually take the limit of these two terms. We can take the limit of sort of less complicated functions. We're sort of breaking up the complexity of a certain function so that we can sort of individually evaluate the limits and sort of break up the problem and make it less complex here. So that's our third property. Let's move on to the fourth property. In the fourth property, all the rest of the properties in this sequence, they're all going to depend on this rule, on this precondition, I guess, that the limit as x approaches a of f of x and the limit as x approaches a of g of x, that they both exist and they're both finite. So now let's say that if we took, instead of the sum, if we took the limit as x approaches a of f of x times g of x, if we had the product of these two functions, then that's going to be equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. So this is like saying, just like we said in the last part, that the limit of a sum was the sum of the limits, what we're saying here is that the limit of a product is equal to the product of the limits. We can sort of, again, we can distribute, if we look at this limit, we can look at this as a limit operator. We can distribute that operator amongst these two functions. And again, you can see that what we're doing is we're breaking down this limit problem into something, we're breaking down the complexity of it. We can take the limits of two things that are less complex. F of x is less complex than f of x times g of x, and similarly g of x is less complex than f of x times g of x. So anyway, that is the fourth property. Now let's move on to the fifth property. And now both the fifth property and the sixth property, they're going to depend on one more rule. We're going to have to say that the limit, and let me just make these, I'm just going to say the limit of g of x here. We're going to have, the next, I guess, precondition that we're going to say in this part is that the limit as x approaches a of our function g of x cannot be equal to 0. We can choose any other function that we want, except for, it can be equal to any other value besides 0 for these next two rules to hold. So now the first rule, or I guess the fifth rule that we're going to talk about, is we're going to say if we took the limit of a function, if we took the function as x approaches a of the function g of x, and we were to raise that function g of x to some power, and it could be any power, including 0 or including a negative power here, because we've established that the limit as x approaches a of g of x cannot be equal to 0, it can be any power, either positive or negative, that this is just going to be equal to, and again, what we're going to see is we can move because this constant does not depend on this constant does not depend on x at all. We can just move this limit operator past this power. We can move it past, I guess, this part of the function. So this is going to be equal to the limit as x approaches a of g of x, all of that raised to whatever that power is. And keep in mind, this can work for any power k that we put in here, so long as we have this precondition, so long as we know that that the limit as x approaches a of g of x cannot be equal to 0. So if we add, the limit as x approaches a of g of x raised to the -1 power there, we would have, that would be, it would be like it would be like 1 over. Let me actually just do that example real quick. If we said we had the limit as x approaches a of the function g of x, all of that raised to the -1 power, then that would be equal to, we can say that that's going to be equal to, let me actually let's rewrite this as 1 over the limit as x approaches a of the function g of x. We can only say that because we know that this part of the function, that this limit isn't equal to 0, right? If it was equal to 0, this wouldn't hold because we'd be dividing by 0, or we could be dividing by 0 there. So we need that precondition there. We need that condition that our limit here cannot be equal to 0. However, and you might also realize this, if we took the limit of some other function as x approaches a of f of x, and we were to raise that to the k power, we could say that the limit as x approaches a of just f of x could be equal to anything including 0, and we can move this limit past. So we could say the limit as x approaches a of f of x, all of that raised to the k power. We can say that these two things are equal as long as this number k has got to be a positive number. K has got to be, or it's got to be greater than or equal to 0. K cannot be a negative number if this limit as x approaches a of f of x is going to be equal to 0. And hopefully that's obvious why that is, because if we did have this limit as x approaches a of f of x being equal to 0, then we would have a situation where we were dividing 1 by 0. So anyway, hopefully that makes sense. We'll do an example of that in maybe the next video, just to sort of illustrate that point. And now for the last property of limit. This is going to be property number 6. And remember that our precondition, that the limit as x approaches a of our function of g of x cannot be equal to 0. That's our precondition here. We're going to say that if we took the limit as x approaches a of f of x divided by g of x, that this is just going to be equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. So this is like saying the ratio or the limit of a ratio is equal to the ratio of the limits. Again, you can say that we're really just distributing this limit operator into these two functions. And remember that we can only concretely say this when we have this precondition, when we have this condition that the limit as our function, or the limit of the function g of x as x gets really close to a, can't be equal to 0. Because if we didn't have that, then we could have a situation where we were dividing by 0. Anyway, I'm out of time in this video. In the next video, I'll start doing some examples that kind of illustrate these properties. So anyway, thanks for watching, and I'll see you soon.